Hello everybody and welcome to another HD DWF arcade repair. I received two game boards of Missile Attack, which is a bootleg of Atari's Missile Command. The bootlegs are made in Italy by U.Games. In this episode we'll see the complete repair process of the first of the two PCBs. First of all, let me quickly introduce this bootleg PCB. The top part is almost identical to the original Atari PCB game. Even the IC position are the same as far as I could check, so I can use the original Atari schematic for troubleshooting. As always, links to all the useful files are in this video description. However, this clone lacks the custom Atari Poki integrated circuit that's used in the original PCB to generate the game sounds and to read some of the configuration dip switches. In this bootleg, the sound generation part has been substituted by two EEPROMs that contain 4-bit digital samples of the sounds that are applied back by addressing and scanning these EEPROMs with TTL counters and a few other glue logic ICs. The dip switches are read by using a common 74LS244 buffer IC. I have reverse engineered part of the sound and the dip switch read circuit during the troubleshooting of the two boards. Another substantial difference is in the video output circuitry. First of all, the red, green and blue levels are inverted by using the inverting outputs of the LS175 latch. Also, the composite sync and composite video auxiliary outputs are entirely missing, so I will have to at least obtain the composite sync signal with a small external circuit. The last important difference is on the audio output section. The usual Atari balanced low-level audio output is not present. Instead, there is an integrated audio power amplifier on the PCB with a direct speaker output. This board shows some physically damaged parts. This capacitor has a lifted leg. This other one a broken leg. And also the crystal seems broken. But there is no sign of previous work on it, however. So I've just soldered back the lifted capacitor, replaced the one that had a broken leg. Indeed, the crystal had a broken pin, but luckily it has a very common frequency, so it was replaced with a spare one. Then I've dumped all the ROMs and compared their content between the two PCBs. So I'm quite confident that they are good because I found no differences between the two game boards. I'm now going to verify the ESR of every electrolytic capacitor. This one, for example, is okay. This one looks bad, so I'm going to remove it. All the others look reasonably good. And yes, that one was totally bad. It should be 10 microfarads, so it would be replaced. Finally, I've retinned the contacts that carry all the power rails on the edge connector, and of course I wired a suitable connector with the needed power supply voltages for this board, so I'm ready to power it on and check the CPU vital signals. The reset signal pulses. This means probably that the watchdog timer is not being properly reset. The clock signal, however, looks good. This arcade game uses a 6502 CPU, so the first thing I can do to troubleshoot the board is using a NOP generator. This will allow me to check all the address decoding logic and the address bus buffers. So, first of all, I'll check every ROM enabled pin for activity. All of them are pulsing. Then I check the address decoders. So far, nothing looks like stuck or invalid. Now, since I didn't find any obvious fault with the knob generator, I thought I'd use my in-circuit dynamic RAM comparator that I made some time ago when troubleshooting some Commodore PET mainboards. In those occasions it worked very well. Links to the relevant videos are in this video description. So, to make a long story short, I found two ICs where the error line was pulsing all the time, so I thought I'd remove those two ICs. However, both the dynamic RAM ICs were good. Luckily, I could just reinstall them into the sockets. Having designed myself the dynamic RAM comparator, I know very well what conditions must be true for it to give meaningful indications. Both these conditions were true when I successfully found the bad dynamic RAM ICs on the Commodore PET repairs. The first condition is that there must not be continuous reads from uninitialized RAM. Now, this game video RAM and the CPU working RAM are just different ranges on the same ICs, so the video generator is continuously reading from the dynamic RAM, but since the CPU is not executing the correct code due to a fault, the video RAM is never initialized, and the hardware comparator just gives absolutely random results. Using it was then a big mistake I made. The second condition is that we must exclude any address bus or data bus issue on the hardware under test. We'll see later if this one was true or not. I've decided at this point to write a quick RAM test code to help me identify what was wrong on this board. As I often did on other arcade repairs, I just copy some random data into the relevant RAM segments. Then I read back the data from RAM and compare with the random data from the test ROM. As test outputs, I'll use some game outputs that I can drive from my test code. To properly run the diagnostic code, I will also ground pin 13 of UD8 to disable the continuous watchdog resets. The code is very simple. I will only test page 0, page 1 and page 6 of the RAM memory, since they are for sure used by the game code. If any of these pages contain an error, the game will not run properly. The code then stops at the first mismatched byte and reports only the highest failed bit, but that should already be enough to give me some hints. So I've used a 2816 EEPROM, and it must go in place of the first EEPROM that contains the reset vector. Pin 19 is high, it means the code found errors. Now pin 9 is 0, pin 6 also 0, pin 12 is 1. So, according to my code, this indicates that data bit 2 is bad. So I've decided to remove the IC going to data bit 2. and I've replaced it with one of my spares. But we get the same exact result, bit 2 bad. So clearly I've not done my troubleshooting procedures very well this time. I've checked for conflicts on the CPU data bus pins and I found no problems. But in this game, the data path is split in two by this LS244 transceiver. On the CPU side, the data bus can work both in read and write cycles. But on the other side of UE2, the buffered data bits are always driven, so it's a write-only bus. And sure enough, high current on pin 5. And also on pin 16. Now, pin 5 and pin 16 are both on the write-only bus and correspond to bits 2 and 3, so at least my test code was giving a good indication. To be fair, I checked from the beginning this other bus transceiver. This connects the dynamic RAM ICs to the CPU data bus, but it's enabled only during read cycles and not on write cycles. And I couldn't find any issue on it anyway. At this point, I wanted to check with the oscilloscope how all the buffered data lines look like. This is D0, D1, and this is D2. Notice a little step on the lower level. D3 also shows the little lower step. D4 to D7 all look normal. Really, the only clue would be this small step on the low lever, which is not easy to notice, and so far this looked like a very strange fault. But finally I found the real problem. Look at this. The two buffered data lines are shorted together. So I've made a list of all the ICs getting both the buffered D2 and D3, and I'm searching with the current tracer for the other IC that's getting the high current. But none of the IC is showing high current on D2 or D3 pins. Since it is not a shorted IC, it must be a physical short somewhere else. So now I'll search for the minimum resistance value on the ICs that are connected to both D2 and D3 to get near the problematic area. And here it is, a scratch that created at least one short circuit. When PCBs are made without the solder mask, this may happen when a probe or a screwdriver slips. To correct the problem, I just apply some flux over the damaged area. Then I pass over the traces with the solder iron and a fine tip and reflow the tin. Of course, the flux residues would be cleaned with the isopropyl alcohol. Now let's check if the short is gone. Yep, so far so good. Now it's time to connect the video output. I will just use the inverted RGB signals, since my little Sony monitor should cope with them. I surely just need to play with the brightness controls. However, I need to obtain a composite sync out of the separate vertical and horizontal sync signals. I'm just going to use an OR gate with a small series resistor on the gate output. I also need to enable the game test code, that is the original Atari test code. However, in this bootleg, the test switch input is not routed to the edge connector, but I could trace it back from the LS244 buffer to one of the DIP switches present on the PCB. And yes, that's a big progress. The test screen indicates no RAM errors, but it says bad ROM and bad chip. Of course, the bad ROM is because this bootleg needs a slightly different code to account for the missing POKEY chip. And the bad chip is exactly because the diagnostic is trying to access the non-existent POKEY. Now, to properly test all game inputs, I will need a trackball, and of course I don't have the original cabinet here. However, it seems that the interface just expects the signal coming from a couple of very common quadrilateral encoders, one for the horizontal movements and one for the vertical movements. So I searched in the spare PCB boxes for an old ball mouse PCB, and here we are. I already removed the old control IC, since I'm only going to use the outputs directly from the 4 phototransistors that are mounted around the encoder wheels. Basically, I need to provide the power for the 4 infrared LEDs. Then the suitable outputs can be taken directly from the phototransistors collectors or emitters, whichever is connected to a pull-up or pull-down resistor. There are 2 LED phototransistor pairs for each wheel. One of them will be the clock and the other will provide the data signal for one direction. It is not important which one we choose as clock or data. All it can happen if we swap the two signals is that the movement will be inverted with respect to the wheel rotation. So I connected the power wires and the 4 data wires to the proper pins on the edge connector, and I'm ready to test the game inputs. However, the cross-shaped cursor is stuck, no matter how I rotate the wheels. So, to troubleshoot this issue, I must debug this rather simple circuit. First of all, we must verify that each of the 4 inverter inputs have the correct DC bias of about 2.5 volts. And sure enough, in this board the bias was missing, because a couple of these 10 kilo resistors had broken solder joints, so just reflowed all of them, but that did only restore the vertical movements and not the horizontal ones. The next step, once we have verified the correct input bias, we must verify that the CMOS inverter outputs toggle as we rotate the encoder wheels. Output 8 and 12 must toggle when we rotate the horizontal wheel. Here is pin 12 and it toggles as I rotate the wheel. Also, pin 8 looks good. Then we check the outputs of UD9. In case of the horizontal movements, pins 9 and 12 must toggle when rotating the wheel. Okay, pin 9 is toggling. And 12 is definitely stuck. Okay, I see. The input on pin 14 is floating. So we have just found that the connection from pin 12 of UC9 to pin 14 of UD9 is broken somewhere. So I've just reconnected the 2 pins with a small insulated wire. And finally, both the horizontal and vertical movements work fine. So I can exit the diagnostic now. And here is the attract mode of the game. In the end, this was a less than perfect but successful repair. I hope it was interesting and that you learned something. If you have any question, please use the comment section below. That's all for this video. Have a nice time and thank you for watching.